All right, ladies and gentlemen, welcome to another exciting chemistry lecture here. We are now looking at chapter 6, lecture number 1. This is the lecture on thermochemistry, energy, and work. Let's get started. So here we begin our conversation around the world of thermochemistry. Thermochemistry is the field of chemistry that deals with transformation of energy during chemical reactions. And energy is a topic you've probably explored from back in your days in physics in terms of how we look at energy from a chemistry standpoint. We're going to kind of take some familiar ideas from your days in physics and then some new ideas that are going to be entirely new to you in the world of chemistry and use them to come to an understanding about how chemical systems can be used to do useful work for us. So we'll start off here with some definitions. Our first definition here is a definition for energy. Energy is a familiar concept, but defining it can be a little bit tricky to do. So we see that we need to use energy to do all the things we do in our daily lives, from running our own bodies to heating our houses to moving from place to place using transportation. But it's kind of an unfamiliar quantity to talk about measuring energy or defining it specifically. So how I'd like you to think about energy in this particular class is as the capacity to either do work or to produce heat. Now, something that I'm sure you're familiar with from back in previous science classes is the idea that energy can neither be created nor destroyed. And that concept is what we refer to as the law of conservation of energy. And even though that energy can neither be created nor destroyed, you can transform energy from one form into another. Now, when we talk about transformations of energy between different forms, from your physics days, this is probably a familiar idea in terms of the transformation of energy between potential energy and kinetic energy. And when we say that word potential energy, probably the first thing that comes to mind is thinking about an object which is high up off the ground, which therefore has gravitational potential energy. Now, obviously, in the world of chemistry, we're not going to be interested in the amount of gravitational potential energy that objects have, because nobody's really going to be asking you chemistry problems about what happens if you move a beaker higher up off the ground. So we want to kind of broaden our definition of what we really mean by potential energy to encompass chemical systems. So when we talk about potential energy from here on out, I want you to think about potential energy as being energy associated with position of an object. Now, that can be, like, as we'd mentioned, gravitational potential energy. The higher you put an object up off the ground, the more potential it has to gain kinetic energy as it falls. So we would say that object has gravitational potential energy. But for chemical systems, you might consider the relative position of ions with respect to one another. If we have a crystalline lattice where those ions are close together, that would be a relatively low potential energy configuration of those ions. And we know that's true because it would require energy for us to pull them apart. That is, we would have to do work to separate those ions apart from one another. So the separation of ions is essentially a property which is going to affect the chemical potential energy of a system. So potential energy is energy associated with position, and the other type of energy we're going to talk about is kinetic energy. Kinetic energy is energy we associate with motion. So again, thinking back to your physics days, we consider like a ball flying through the air as an object which possesses kinetic energy that is a function both of its mass and its speed. And you might remember an equation from way back in your physics days, which is kinetic energy is equal to 1/2 mass times velocity squared. So that's how we calculate the kinetic energy of an object. And if you think about it, you can treat little tiny individual atoms or molecules themselves as simply just moving objects through space. And as those objects have both mass and speed, that would imply, therefore, that molecular systems will also have kinetic energy based upon the motion of those particles as well. And we can transform what has been initially potential energy in the form of potential energy within a chemical system into kinetic energy, and we see that come about as the evidence that we see when chemical reactions occur. As you have observed in the past, chemical reactions sometimes release energy into their surroundings, which implies, therefore, there must be a change of the potential energy of that system, because we see an increase in the kinetic energy of the particles. That is, if they're at a higher temperature and they release heat, we see that heat essentially as being motion of those molecules. So again, Chemical systems have both potential and kinetic energy, and we can transform between those different forms as chemical reactions occur. All right, now in terms of transferring energy from place to place within a chemical system, we can transfer energy in two different ways. And both of these should be fairly familiar to you. Number one, we can transfer energy via heat. We define heat as being the transfer of energy as a result of a difference in temperature between two objects. And that heat generally tends to flow from areas where it is hot to areas where it is cold. And that transfer of heat energy is essentially a result of the random molecular motion. That is, those particles within a system have kinetic energy, they're moving, and because they're moving, they bump into things and they can transfer that kinetic energy via collisions between particles to other parts of that system. You can think of heat as kind of being disorganized energy transfer. It happens just due to the random motion of the particles. Now, that's in contrast to the other way we can transfer energy, which is by doing work. Whereas transfer of energy by heat flow is essentially a random process that results in energy moving from high temperature to low temperature areas. The process of transferring energy by doing work is very much the opposite, that it is organized. To do work, you have to exert a force on an object over a distance. And you might remember that equation from back in your physics days, that we can calculate work by taking the product of force times distance. And we see that we can do work on objects by, say, taking a ball and lifting it up into the air. In order to lift it up into the air, we have to exert a force on that ball over some distance. And we know that that object has had work done on it because as it moves higher and higher up into the air, it therefore would gain more gravitational potential energy. So again, work is a means of transforming energy in an organized fashion, whereas heat is a transformation of energy as a result of temperature differentiation, which is inherently disorganized. Now, that being said, I want to be very, very careful to make a distinction between two related but different concepts, and those are the ideas of heat and temperature. We just defined heat for you as being an amount of energy transferred by objects via thermal motion. So think of heat maybe as like the total sum energy moving from place to place as a result of those collisions between particles. Now that's very, very different from temperature. And to give you an example as to why, have a look at the pictures that we have on this page here. On this page, I have pictures of two different systems, both of which exist at the same temperature. On the top, we have a boiling lake in the country of Dominica, and that is literally a lake of boiling water. And on the bottom, we have a boiling pan of water. Now, both of those exist at the same temperature. That is, they're at the boiling point of water, which is approximately 100 degrees Celsius, depending upon what the pressure is. So if they're both at the same temperature, we can obviously tell that one of those two systems has a much greater capacity to transfer energy via heat flow. Because you can imagine that I could melt a very, very small number of ice cubes in that hot water in the boiling pan right there if I took it off the pan and threw ice cubes in it. But I could melt an enormous number of ice cubes by throwing it into that very, very large boiling lake. And the reason why that's the case is because there's a much larger total amount of energy present in the lake than there is in the pan, because there's just more matter present there. And again, because heat flow is essentially the ability to transfer energy via the random molecular motion of the molecules, the more molecules there are, the greater the total sum of energy within that system. So heat is essentially a total summation of energy flow, whereas temperature is a reflection of the average kinetic energy per particle. So within each of those two systems, the average kinetic energy the particles would have would be the same because their temperatures are equal, but the ability to transfer energy by heat would be greater in the large lake because there's just more molecules and therefore more energy overall within that system. Now, one of the concepts that we're going to be very interested in as we explore thermochemistry is the direction in which energy flows, either by doing work or by transferring by heat. And something that's very, very important to understand is that some of those quantities, like work and heat that we deal with, depend upon the pathway which we take via a chemical process. But some properties that the system might have might be independent of the pathway we take. And the idea that we're kind of getting at here is the idea in chemistry which we define as a state function. We define a state function as being a property of the system that depends only upon its present state. That is, it is a path-independent property. And to give you an example of exactly that idea from the regular world before we get into the world of chemistry, let's think for a moment here about the concept of elevation. So suppose you're a mountain climber and you're climbing up one of Colorado's 14ers, and you find yourself at a certain point on the mountain and you use your altimeter to measure the elevation that you're currently at. Your altimeter will give you a reading of the current elevation, and it doesn't matter which pathway you took to get there. The elevation you have is only dependent upon where you are currently standing. And that's a very, very different kind of property than if you would measure it instead of elevation, if you would measure the distance you would travel to get there. So you might imagine that you might take a first pathway that was kind of a meandering pathway that winded its way up the mountain until your current location, versus a direct route that went straight up the mountainside. And depending upon which path you take, you would get a very, very different measurement for the distance you had traveled to get to your current location. So in that example, elevation would be an example of a state function. That is, it only depends upon where you currently are, not upon the path you traveled to get there. That's different from the concept of distance traveled, which is a path-dependent function and therefore is not a state function. That would depend upon how you got to your current location for how much distance you had traveled. So let's take a look here now at a couple of different examples and consider if these are state functions or not. The first one on here in example one is the property of volume. If you measure a volume of a gas system, like let's say you've got a piston which can expand and contract, and you can measure the volume inside of a cylinder, the volume of the system does not depend upon what it used to be in the past, whether you expanded to get to that volume or if you had to contract the system and compress it to get to that volume. The volume you would measure, you would get would be the same regardless of how you got there. So that means volume, therefore, would be an example of a state function. The same would be true of temperature. Temperature is a path-independent function as well, because if you measure the temperature of boiling water, which is 100 degrees Celsius, you don't know whether that boiling water, to get to the temperature of 100, had to be heated up over a very, very long period of time, or if it had to be cooled down from a much higher temperature and condensed from gas phase vapors. All you really know is that if you measure the temperature, that's what the temperature currently is. So it doesn't matter how you got there, which implies temperature also would therefore be a state function. Now, let's consider next the idea of work. And this one tends to cause people some bit of difficulty. So to come to an understanding about whether work itself is a state function, imagine for a moment that you're building a pathway out of large stone boulders. And so you're working in your backyard and you're moving those rocks around. I think we can all agree that moving heavy rocks is a tremendous amount of work. It requires you to exert large amounts of forces over large distances. But the amount of work you have to do depends upon where you are getting the rocks to build your path. So if you have a quarry of rocks that you can draw from, which is very, very close to where the path is being built, you'll have to do a whole lot less work to move those rocks into their new locations than if your quarry of rocks is at the bottom of the hillside, requiring you to carry those rocks up to the top of the hill. So it logically would state then that the amount of work you have to do to create your pathway would depend upon the pathway you take to do that work. So work, therefore, would be a path-dependent function, and therefore it is not a state function. Same sort of idea would apply as true to heat. Because remember, whereas work is a means of transferring energy that is directional and essentially organized, heat is also a means of transferring energy as well. And so the amount of heat that would flow to go between two different points of states of a chemical system would depend upon where you start. So that is to say, if I was measuring the current state of the system and I had started with a system that was much, much hotter, to get to the current state of the system, I would have had to have transferred heat out of the system. Whereas if my initial conditions for the system was colder than where I currently am, to get to my new position, I would have to transfer heat into the system. So depending upon where you start, you would see a different flow of heat either into or out of the system to get to your current position, which again implies heat is also a path-dependent function and therefore not a state function. And here's where the real trick comes in here. How about energy? So we understand that work and heat are both ways of transferring energy from place to place within a system. But energy itself is very, very different. And to understand that here, think for a moment about a simple system rather than a chemical system. Think again about a soccer ball flying through the air. That soccer ball flying through the air has some amount of kinetic energy associated with its motion. It also has some amount of potential energy based upon the height above the ground that it actually is. But even though that soccer ball has both potential energy and kinetic energy, the total energy of that soccer ball, the sum of its kinetic and potential energy, is only dependent upon its current state. That is, you have no idea necessarily what had happened to that soccer ball beforehand. The energy you would measure is wholly dependent upon how fast it's traveling right now and how high above the ground it is right now. And because of that, that implies, therefore, that the internal energy of that system is therefore path independent. It does not matter the path you took to get there, all that matters is the current state. And therefore, energy itself is a state function. So work and heat are not state functions, but energy is a state function. So now we see that there's multiple different ways you can transfer energy within chemical systems. You can use a chemical system to do work, or you can do work on that chemical system, or you can see energy flow into or out of that system via the flow of energy as heat. Now, because what we're interested in chemical reactions is understanding the movement of that energy from into or out of the system, we're going to be talking about dividing our universe up in the world of thermochemistry into two distinct parts. Number one is what we refer to as the system, which is really the chemical reaction we are currently examining. And number two, the other part of the universe we're going to divide up here is what we refer to as the surroundings, which literally is everything that's not in the system, the entirety of the rest of the universe. And we want to understand how various different chemical processes can either transfer energy from the surroundings into the system or from the system into the surroundings. And these are some familiar terms you probably remember from first year chemistry here. We define a chemical process that shows a flow of energy from the system into the surroundings as an exothermic process. And that prefix there, exo, literally means beyond. So essentially means that energy flows from the system to the beyond. So it moves out of the system. The opposite of that exothermic process, where energy flows from the surroundings into the system, would be referred to as an endothermic process. Now, one of the difficulties that people tend to have when thinking about exothermic versus endothermic processes is to remember that in most cases, you are not part of the chemical system. You are usually part of the surroundings unless your chemical reaction has gone horribly wrong. So if you're doing a combustion reaction, you very definitely do not want to be the thing which is burning. So if you are part of the surroundings, we have to kind of tweak how we look at things because we aren't going to be looking at things from a first-person perspective here. We're going to be looking as an outside observer in the surroundings at the system. And that makes things sometimes seem a little bit backwards in terms of energy flow. So considering it from that perspective, if we see an exothermic chemical process where energy flows from the system into the surroundings, to us, as a part of the surroundings, that exothermic process should feel hot. Because again, as we are part of the surroundings, that means heat is flowing from the system into us. So a process like burning a candle would be therefore an exothermic chemical process because energy is being moved from the system to the surroundings, and therefore we feel that as a hot thing. Now in contrast, an endothermic chemical process is a process where energy again flows from the surroundings into the system. If you have an endothermic chemical reaction taking place within a beaker and you hold on to that beaker, that endothermic chemical reaction will feel to you like a very, very cold event taking place because, again, you are part of the surroundings. And that implies, therefore, energy is flowing from you in the surroundings into the system. So again, exothermic processes feel hot from the surroundings perspective. Endothermic processes feel cold from the surroundings perspective. And what you see here on this page are a couple of different graphs. Each of these graphs is what's called like a reaction profile graph. On the x-axis, we show the progress of the reaction as time passes, and on the y-axis, we see the energy state of the system. Now, for an exothermic process, remember the system is going to be releasing energy into the surroundings, which means the state of internal energy of the system would be higher under the reactant conditions than it would be for the products. So we see a curve here for this reaction profile graph of an exothermic process that starts off at high energy and then goes to low energy. And you notice here on this curve, it's not a straight pathway from high to low. There's a little bump at the very start. That bump that you see at the top of that curve right there is what we refer to as the activation energy for a chemical reaction. And what we mean by activation energy is kind of a familiar idea. If you think about a match will burn via a very, very highly exothermic process. That is, we should see the system start at a high energy and end up at a low energy. But in order to get that chemical process started, we have to supply some amount of energy to the system to initiate the reaction by striking the match. And that addition of energy, that addition of kinetic energy from friction by striking that match, is essentially what gets the reaction rolling. It's very useful actually to kind of think about this whole process as being what would happen to like a soccer ball lying on a hill. If you have a soccer ball on the hill, it's obviously at higher potential energy over here on the left side of our reaction profile graph there, at the reactant side. And it would be at lower potential energy and therefore a more stable position for the soccer ball to be in if we were down at the bottom of the hillside at the right side where the products are. But again, the soccer ball will not just roll down the hill on its own unless you provide it with the initial energy to get up and over that little barrier of the hill at the start. So that little kick you have to give to the soccer ball to get it up and over the top of the hill is again essentially akin to the activation energy for that system. Now, on the second graph right here, for the endothermic graph on the right, again, we have the same sort of idea here, which is that as the reaction progresses, there's a change in the internal energy of the system. But for an endothermic process, recall that the system is absorbing energy from the surroundings, which implies the internal energy of the reactants is lower than the internal energy of the products. And so we end up with a reaction profile graph that looks something like this. Now note here, folks, it might be kind of familiar to come up with a lot of examples of exothermic reactions you see around you. We see things like candles or the combustion reaction that takes place inside of your car, or you even could think about the reactions that go on inside your body to produce heat. If you hold your hand up in front of your face, you'll feel your body radiating heat into your surroundings. So the reactions involving cellular respiration themselves are also exothermic chemical processes. But coming up with a whole bunch of examples of endothermic processes is a little bit trickier. And the reason why, actually, as it turns out, is that endothermic processes are less common in nature. And we can understand why that's the fact by, again, having a look at that reaction profile graph. Recall the activation energy is that barrier we have to overcome to get from our initial starting potential energy level up to the top of that hill, from which point the reaction will proceed spontaneously. And because in an endothermic process, we start off at a much lower energy level overall, that implies that activation energy barriers for endothermic processes tend to be much, much larger than a reaction barrier to an exothermic process occurring. So we see larger activation energies for those endothermic processes. All right, and now that we've seen how we can observe chemical energy flowing between the system and the surroundings, now we can start to consider on the next slides how we can actually make quantitative measurements of energy flow within these reactions. So as we just discussed right here, we see that we can transfer energy between the surroundings of a chemical reaction and the system itself. And what we're going to be looking at now is how to quantify those movements of energy between the system and the surroundings. So the topic we're going to consider right now is an idea called the internal energy of the system. We define the internal energy as essentially the total sum of both the kinetic energy plus the potential energy of the chemical system. Now, something that's important to note here is that we don't really have a device that allows us to directly measure the internal energy of a system. That is, there is no energometer. We have thermometers which measure the average kinetic energy of the particles inside the system, but they don't tell us anything about the potential energy of those particles. So measuring internal energy as a pure quantity is a very, very difficult thing to do. It's a much easier thing to approach rather than trying to measure the absolute internal energy of the system, to measure changes to the internal energy, either by measuring the flow of heat or the work done on a system. So we're going to be more often than not talking about changes in internal energy rather than the absolute value of internal energy overall. We can either change the internal energy of the system, either by seeing heat flow either into or out of the system, or by doing work on the system, or by having the system do work. And that implies, therefore, we have an equation here, which would be the change in the internal energy of the system, delta E, would be equal to the flow of heat, Q, plus the work, W. Now, the sign on those values, Q and W, is the important thing to consider and the number one thing that people get tripped up on for questions on the AP test. Remember, in an endothermic process, heat flows into the system, which implies the system ends up at the end of the process at a higher potential energy than it had been at the start. So that implies endothermic processes involve positive flow of heat. And therefore, the sign on Q in that reaction would be a positive. But for an exothermic chemical process, energy is leaving the system, which implies the system, therefore, is at lower potential energy after the exothermic process occurs. That must mean, therefore, that the change in internal energy for an exothermic process would be a negative value. And therefore, Q, the flow of heat for exothermic processes, is negative. Same logic we can apply to work. If we do work on the system by, say, for example, taking a gas phase system within a cylinder and compressing that piston, that is, again, we have to push on that piston to compress the gas inwards. If we do work on that system, then we've essentially added energy into that system. And because of that, the sign on W for the change in internal energy would be positive. So if work is done on the system ends up at higher potential energy, and therefore W is positive. But imagine the exact opposite process occurring. If that piston, which we have compressed by pushing inwards on it, then is allowed to move back outwards and expand, then the system will be doing work on the surroundings. This is exactly the idea that helps your internal combustion engine in your car cause the car to move. That is, that hot gas, which is expanding inside of the combustion chamber, inside of that little chamber where the piston is held, that hot expanding gas pushes outwards on the piston, and that then causes the system to lose internal energy, which can then be converted into kinetic energy of the parts of your car. So if the system itself does work on the surroundings, then the work done from the system's perspective would be negative. So paying attention to the sign on those variables, Q and W, heat and work, is by far the most important thing you have to be watching for on your AP problems for thermochemistry. Now have a look at the picture that we've got right there. In our chemistry lab right there, we've got a delightful picture here from Halloween of a pumpkin, which seems to be experiencing a fairly exothermic reaction around it. Because that exothermic process of burning that pumpkin is releasing a large amount of heat into the surroundings, that would imply, therefore, that Q for the system would therefore be a negative value. That is, the heat is flowing out of the system into the surroundings. And again, be very careful there because it's easy to get tripped up. We have this kind of internal desire to want to make hot things positive, but remember, we're always looking at this from the system's perspective. So we, again, as the part of the surroundings, feel it as being hot because we're absorbing that energy. But if we absorb that energy, that means the system must be losing it. So from the system's perspective, Q would be negative for that reaction. So now that we are going to start trying to quantify changes in internal energy of chemical systems, we need to have a brief moment here to talk about units of measurement. The easiest way of approaching energy units is to look at it from a perspective of work. Remember, work is simply a means of transferring energy and can be accomplished by exerting a force over a distance. Now, thinking to units of force, recall that forces can be measured by calculating a mass times an acceleration. That's from your equation F equals ma from back in your physics days. Masses are measured in kilograms, and accelerations in SI units would be measured in meters per second, or meters per second squared. So again, if I have force, that would be therefore a unit of a kilogram meter per second squared, which would then be multiplied by a distance, which again would be meters. So that would give me kilograms meters squared per second squared, and that unit of kilogram meters squared per second squared is what we define as a unit of a joule. A joule is a relatively small amount of energy. It's about the amount of energy you would be expending by, say, picking up a marker and moving it about a foot higher or so. So not a whole lot of energy. So with that being said here, let's go ahead and now take a look at quantifying an energy flow for a system. For example 2, it asks us here to calculate the change in internal energy of a system, which undergoes an exothermic chemical process in which 22 kilojoules of heat flows out of the system and 5.6 kilojoules of work is done on the system. So again, our equation from the previous slide would be the change in internal energy is equal to the sum of the heat flow plus the work done. Pay attention to sign. This is the only place really where we can have this go astray. Recall this is an exothermic chemical process, which implies, therefore, our sign on the heat flow of negative 22 kilojoules would be a negative value. That is, from the system's perspective, energy is leaving the system. So delta E would therefore be equal to the heat flow Q of negative 22 kilojoules plus, and now here take a note again of the sign on this, we have 5 kilojoules of work being done on the system. So if you do work on the system, that is, you're adding energy into that system, that implies the work done on the system is a positive value. So we have negative 22 kilojoules plus 5.6 kilojoules. And negative 22 plus 5.6 would give us negative 16.4 kilojoules as the total change in internal energy of that system, which implies the system, therefore, would be at a lower internal energy than it was originally. And again, note here, we don't know what the absolute value of the internal energy of the system actually is. All we've calculated here is a change in that internal energy of the system. So here we now come to really the heart of the matter as to why thermochemistry is an important concept for a chemist. We can use chemical systems in order to do useful work for us, and we see that in the world around us all the time. It can be as crude of a system as an internal combustion engine, where we are essentially burning a fuel to cause our car to experience motion, or it can be a relatively more complicated chemical system where we see work being done by electrochemical reactions involving batteries. So where I'd like to start here is with a relatively simple chemical system, like inside the internal combustion engine in your car, where we see the movement of a piston due to the expansion and compression of gases inside of that chamber. So we're going to be looking at work here done by expanding and compressing gases. Work can be done by a gas on the surroundings as that gas expands outwards. That gas expanding outwards would push the piston outwards, which could then cause the movement of the crankshaft and the car will move forward. But at the same time, we could also compress the gas, and in order to compress that gas, we would have to push that piston inwards, which means that we could also be seeing work done on the gas. So again, this is what we call expansion compression work. Now, to derive an equation for expansion and compression work here, let's start by taking a look at some definitions from back in physics days here. First of all, let's talk about what we mean by pressure. Recall from our gas law unit that we define pressure as being a force exerted over a surface area. So we've got that first equation there, which is P equals F over A. Pressure is force divided by surface area. Recall from also earlier in physics here that we define work as being a force times a distance. Now let's take those two equations together here for a moment and think about how we can manipulate them. If pressure is force divided by area, then force would therefore be pressure times a surface area. I can then insert that definition of force into the equation for work, which would give me a new expression, which would now be work is equal to force, which is really pressure times area times distance. Now, if you think about that piston expanding and compressing, if that piston is moving upwards and therefore doing work on the surroundings as the gas expands, the distance that that piston moves is really the change in the height of that piston within that chamber. So my new equation here will now be work is equal to pressure times area times the height. Now, a real quick regrouping of that equation, you'll see here that area times height is really the volume of the gas within that chamber. And again, because the position or the height of the piston within that chamber is changing, that would imply, therefore, that the work done by this system on the surroundings would therefore be equal to the pressure times the change in volume of that system. And if you think about that equation, that's essentially the kind of three-dimensional analog of work. So work is kind of like a two-dimensional property as you've looked at it from physics, that is force times a distance. But if we expand that out into 3 dimensions, really a three-dimensional analog of force is pressure, and a three-dimensional analog of a distance change is a change in volume. So that's where we kind of see that these chemical systems can be used to do work as a gas expands. Now, with that being said, think again for a moment about the signs involved in this here. Because an expanding gas causes work to be done by the system, and for the expanding gas, because the change in volume is positive, that must imply, therefore, that the work done by that system is negative, because again, from the system's perspective, if you're doing work on the surroundings, the system's internal energy must be decreasing. And from that, we thus derive here this equation for work done by a system, which is work is equal to minus pressure times the change in volume. And again, that minus is there because from the system's perspective, it is doing work on the surroundings, and therefore it is losing its internal energy. Now, the opposite would therefore be true for a compression. For a compression, work would be done on the system, and if you compress that gas by pushing downwards on that piston, that would imply that the change in volume of that gas would be a negative value. And therefore, the equation W equals minus P delta V would give you a minus pressure times a negative change in volume, and minus a negative yields a positive. Thus, the work done on the system will yield a positive value, and the change in internal energy of the system as a result of that compression would be a positive value as well. So again, you see here yet again another example of the idea that paying attention to the direction of energy flow, and therefore the sign on those values, is of the utmost importance in these equations. So that calculation you have right there is oftentimes referred to as minus P delta V work. Again, it's always from the system's perspective. Work done by the system would be negative. Work done on the system would be positive for these expanding and compressing gases. All right, and to finish up our introduction here to work and P delta V work in particular, we're going to look at a problem which is kind of a doozy here. So bear with me here as we work through example number 3. This is a very, very complicated system which involves both heat flow and expansion compression work. So read along with me here. If we have 1.00 mole of gas phase water vapor at a pressure of 1 atmosphere and a temperature of 100.0 degrees Celsius, the volume that occupies is 30.6 liters. Now, when 1 mole of water vapor is condensed into liquid phase water at 1 atmosphere and 100 degrees Celsius, we see a release of 40.66 kilojoules of heat from the system into the surroundings. Now, giving you a couple other quantities here, the density of water at that temperature and pressure is 0.996 grams per cubic centimeter. And we would like you to calculate here the change in internal energy of the system for the condensation of 1 mole of gas phase water to 1 mole of liquid phase water at that temperature and pressure. So, starting off, let's just go ahead and identify all the variables which we've been given here, and then think about what equations we might use to get to our answer that we're looking for. First off here, we've got 1 mole, so let's go and label that N is 1.00 mole. we have P equals 1.00 atmospheres, and a temperature T is 100.0 degrees Celsius. And we'll go ahead and also label here a volume of 30.6 liters. And now the next one here is important, the heat flow. Notice here that this is 40.66 kilojoules of heat is released. That implies that this is an exothermic chemical process. And as this is an exothermic chemical process, let's go ahead and label that variable as Q equal to negative 40.66 kilojoules, implying again that heat is flowing out of the system. And that negative sign is of the utmost importance here. And then again, we've got a density, so D equals 0.996 grams per cubic centimeter. And we're looking to solve for our change in internal energy. That would be delta E. So we have now gone through and identified all the variables we've been given here. Let's now start by thinking about some equations that we can deal with. First off, our equation for the change in internal energy of a system. We know that the energy of the system can change either by the flow of heat or by doing work, which means delta E is equal to the sum of Q plus W, that is heat flow plus work done. Now, the heat flow in this problem is easy. We've been given here a value for Q. So we can already plug in here a value of negative 40.66 kilojoules for our Q, which really means what this problem comes down to is we need to find the work required to be done to condense that gas. And it very definitely needs to require energy to condense that gas, because remember, if we have gas phase water, we need to compress it to get it into that liquid phase. So this implies that we're going to be looking at some minus P delta V work here. So again, our next equation is work equals minus P delta V. Now the trick is here, we know the pressure that's been given of 1 atmosphere. We need to find the change in volume. We know the initial volume of our system is 30.6 liters, but the final volume we need to calculate. And the key to solving for that final volume is that density of liquid phase water that they've given us here. So let's go ahead and set up a monorail. And we're going to go ahead and start off our monorail here with the amount of water which we have, which is a sample of, again, 1 mole of water. Now I know I'm going to be using my density to get into some units of volume here. So let's first convert our moles into grams so we can then use that density. So setting up our monorail here, 1 mole of water has a mass of 18.01528 grams of water. That again is just water's molar mass. And now to get from grams into volume, I can make use of the density here. My density was 0.996 grams of water per, up top here, 1 cubic centimeter. Now a cubic centimeter, as far as units go, is an equivalent unit to a milliliter. And I'm going to do that so that I can compare like units here. So I'm going to convert 1 cubic centimeter is equal to a milliliter. And then my final conversion here is going to be from milliliters into liters. On the bottom there are 1,000 milliliters in 1 liter. And watching my units there, moles cancel with moles, grams cancels with grams of water, and then we end up with centimeters cubed canceling with centimeters cubed, milliliters cancels as well, and we end up with units of liters here at the end. And as I'm using my calculator here and solving here, I get a volume of that 1 mole of liquid phase water of 0.0181 liters at this temperature and pressure, which sounds to me like a very, very reasonable volume for a mole of water because, again, I know that water is about 1 gram per cubic centimeter, and that looks to me like 18 grams of water would be 1 mole, and that's about 18 milliliters. So that's a reasonable number to be getting here. So after condensing, we'll have about 18 milliliters of our liquid phase water. Now remember here, what we're looking at is expansion and compression work. And so my equation was work is equal to minus P delta V. So what I need to find now is my change in volume of the water sample. And a change in volume can be simply calculated by taking the final volume minus the initial. After compression, we now know my water will occupy 0.0181 liters. And I'll subtract from that now my initial volume that the water occupied in the gas phase, which was 30.6 liters. And that gives me here now a change in volume of negative 30.5819 liters. And I'm going to carry all of my decimals through there so I don't end up with a significant figures issue later on and introduce rounding error. So let's just go ahead and get that in now as our delta V. So I now have the change in volume of that system. In order to calculate the work done on the system to compress that gas, we'll now use the equation work is equal to minus P delta V. Now, note here that I was given a pressure of atmospheres, but I'm going to do a real quick unit conversion from atmospheres into kilopascal for reasons you'll see momentarily. If you recall, 1 atmosphere of pressure is equivalent to 101.325 kilopascal. So that's the value I'm going to put into my equation. So I have minus P delta V is now minus 101.325 kilopascal times my change in volume, which also was negative. Recall I compressed that volume, and that value was again negative 30.5819 liters. And multiplying those two numbers together gets me a positive 3098.7. And my units now are liters times kilopascal, or liter kilopascal. Now note here that that value is positive, which again implies I have to do work on the system to compress that gas and condense it, which obviously makes logical sense. I'm going to have to push inwards on the gas to cause those particles to squish together enough, and as they push inwards, I'm going to have to overcome that pressure, which is pushing against me to keep that from occurring. So this is obviously going to be a positive value now. Now, let's take a look at why I use those units of kilopascal rather than sticking around in units of atmospheres. Recall a kilopascal is simply 1,000 pascal. And remember, a pascal is the international system unit of pressure, which by definition then is a Newton per square meter. So a kilopascal then is therefore 1,000 newtons per square meter. Now remember, a Newton itself was a kilogram meter per second squared. So 1,000 kilopascal, therefore, would be 1,000 newtons, or kilogram meter per second squared, divided by meters squared, and then multiplying that value by liters. A liter in SI units is really equivalent to a cubic decimeter, or 1/10 of a meter cubed. So my new expression now for a liter kilopascal comes out as 1,000 kilogram meter per second squared divided by meter squared times 1/10 of a meter quantity cubed. And you'll notice here, as I rearrange and organize my units there, the 1,000 and the 1/10 cubed cancel each other out. And I end up with units of kilograms meters to the fourth per second squared divided by meter squared, which simplifies down to kilograms meters squared per second squared, which again is a joule. So, long story short, a liter kilopascal is a unit of energy. It is a unit equivalent to a joule. And therefore, the work that I've calculated here of positive 3098.7 liter kilopascal is really positive 3098.7 joules of energy, or equivalent to a plus 3.0987 kilojoules of energy. And that then puts me now in position that I can finish off my calculation. Recall, going all the way back up to the top now, again, the change in internal energy was equal to the flow of heat plus the work done. Again, the flow of heat was a negative 40.66 kilojoules because, again, it was exothermic. The work done was work done on the systems. That was a positive 3.0987 kilojoules. And when I add those two values together, I get a total change in internal energy of the system of negative 37.56 kilojoules. And there you go. That problem is a mess of logical conceptual problems, paying attention to the signs of the heat flow and work done, and also a big old mess of unit rearrangement and organization. So please make sure, folks, the best hint I can make to you about solving energy problems is you have to have incredible attention paid to details about little things like units and signs. All right, so that's it. Thank you for listening here. I hope you enjoyed the mess of that problem there for the end of our lecture here. And we'll move on after this lecture into the next discussion of calorimetry in Chapter 6, assignment number 2. Thanks for listening. Take care.